Okay, so here are my problems that I will be explaining for all the tasks 5 through 12. This first one goes over checkpoint 5 and 7, which is internal laminar friction loss and Darcy's law. So I have the laminar friction factor of this water trickling down through a porous media. Um, and then you will rearrange that equation to solve for the velocity once you find the friction factor. You can find the friction factor through Bernoulli's equation, and it turns out to just be g times z. Plug that into to solve for velocity. And once we have velocity, we can solve for the volumetric flow rate and the Reynolds number. And the Reynolds number needs to be quite small, under 10, and it is with a value of 3.6, which proves that it's laminar going through this porous media in the water filter. This next problem is going to be turbulent flow, friction loss, as well as I threw a pump in there to cross out 2 and do a pump analysis. So I gave the net positive suction head for the pump analysis, and I gave the volumetric flow rate for the friction factor. So first you can find velocity and Reynolds number using the volumetric flow rate, which shows it's turbulent. And then to find the friction factor, you have to sum up all the minor head losses. And then you can plug that into Bernoulli's equation, and eventually we will solve for Z2, which will be the height of cavitation. And we know the net positive suction head will equal P2 over rho g plus V2 squared over rho g plus minus P sat over rho g at the point of cavitation. So we can plug that into the Bernoulli equation since we know the suction head, and then eventually solve for the height of z of 65.8 feet, which is when it gets that high, it'll cavitate, and that just goes to show why you don't throw the pumps at the end. So the hoses, you put them at the beginning, and then friction factor won't affect that cavitation. This next problem is going to go over checkpoint 8, which is drag, and I'm analyzing a bullet going through 3 fluid mediums, air, water, and ballistic gel. And so I assume the bullet to have a drag coefficient of 0.04. And so you can use that to solve for the drag force, and then plug the drag force in to solve for work. And as expected, the ballistic gel has the highest work and the highest drag force since it's the most dense. That just makes sense. Fairly easy problem on drag. This next problem is going to be compressible flow. And I have propane going through a nozzle. You can look up those known values for propane in table 812, and you assume this flow is isentropic, has a negligible velocity going into the nozzle, and you assume propane gas is ideal. And since it's isentropic, you know P naught is equal to P1, and T naught is equal to T1. And then we can use those values to solve for the critical pressure and temperatures. Once we have the critical temperature, we can solve for velocity, because we know the equation for velocity is equal to the square root of 2cp times change in temperature, which is the T naught minus critical temperature. And then we can divide that velocity by the speed of sound to find the Mach number, and we know the Mach number will be less than 1, which it turns out to be, because going through a nozzle at sonic speed, the velocity cannot be higher than a Mach number of 1 and cannot surpass the speed of sound. And so to find the mass flow rate, there's a couple more calculations. You know, the critical density, which is needed to find the mass flow rate, is the critical pressure over R critical temperature, and then plug that into the equation for the mass flow rate, and you get 93.3 grams per second of propane flowing through the nozzle. My last 2 problems are solving Navier-Stokes. This first one is just analytical, and I have water going through a tube at constant flow, so it's fully developed, it's laminar, there's no slip, no pressure change, it's water's Newtonian, steady state flow, and it's not rotating. So first you have to solve the continuity equation. You cross out anything with dt because it's steady state, and it's fully developed flow, so there's no change in velocity. In the r there's no velocity in the r direction, and there's no velocity in the theta direction because it's irrotational. And that gets that assumption for the continuity equation. You plug that assumption into the z component Navier-Stokes equation, as well as the other assumptions that were made in the continuity equation. If the first derivative is 0, the second derivative is also 0, and that leaves the gravity term and the UZ-dr term. And so now we can apply our boundary conditions and integrate this equation twice. The first boundary condition is a no-slip boundary condition. This assumes there's no velocity at the barriers of the flow, which is outside the tube, and that the maximum flow rate's in the middle of the tube, which states dUz-dr is equal to 0, and that's because it's symmetrical flow. So we integrate once, apply boundary condition 2 to solve for constant 1, and then integrate again after dividing out the r from the right side, and then integrating, applying boundary condition 2 to solve for C2, and we get a nice velocity profile of UZ is equal to rho GZ over 4 mu times R naught squared minus R squared, R being the variable, R naught being the outer diameter of the flow, the inside of the tube. And then finally, with this profile, we can solve for the volumetric flow rate by doing UZ times dA, and in this circular tube scenario, dA is 2 pi r dr. So 2 pi goes with the constants outside the integral, and then you multiply an r to add another exponent. When you integrate, you get the volumetric flow rate is equal to rho gz pi over 8 mu times r naught squared. Plug that in, and you get 1.94 liters per second, which is a substantial amount of liquid flowing through. And that assumption of laminar flow was probably incorrect to make for the scenario. However, it was made. And this next question is for laminar flow of the creek at an angle of 12 degrees. You assume laminar flow, fully developed flow. There's no slip at the bottom of the creek. There's no edge effects are negligible and entrance effects are negligible. The creek's just going down and it's wide. It's also exposed to atmosphere, so there's no pressure drop. First, you solve the continuity equation. Similar assumptions as last time: steady state, constant density, fully developed, and wide. So you get dux dx is equal to 0. And we can apply that to the x component Navier-Stokes equation. And again, if the first derivative is 0, second derivative is also 0, so you can cross out 2 of those terms on the far right, and we finally get simplified down equation of a constant on the left is equal to the second derivative of vx in terms of y. We have 2 boundary conditions at y equals 0. The velocity is 0, so at the bottom of the creek there's no velocity because of no slip. And then at the top of the creek, there's a max velocity, and so the velocity is not changing in terms of z. And this is a special case for a liquid-gas interface since the water is so much more dense than the air. And so again, we're going to do the same process to find a velocity profile, integrating twice, applying boundary conditions to get that velocity profile. And then we're going to use those values with finite differencing in Excel to solve analytically and get a nice graph of this flow as y is changing. And so finite differentiation equation is derived here, with that left value being a constant and that right value being a variable of the velocity above and below the point you're looking at. So for example, at a height of 0.001 meters, you have a velocity of 127.844 due to finite differencing. And so the constant that I mentioned earlier of rho g sine theta delta y squared over 2 mu is 2.166. And then I just add that to the average of the below and above values for the analytical solution, which is in this case 251.35639 and 0. And so I add that, the average of those two, and then Excel does the rest and makes this nice looking graph, which is what it's expected to look like, with a velocity of 0 at the height of 0 and a maximum velocity at the top of the flow.